Welcome to week 2 of physics and our next segment of relativity. Today we're looking at the postulates of special relativity with a focus on the Michelson-Morley experiment, and we're going to talk a little bit more about Einstein as well. Our learning goals today are to recall both the postulates of special relativity, which we're going to be using for the rest of this unit, and we're also going to recall that motion can only be measured relative to an observer. So that's always true, and that's what we were working with last week with our frames of reference. So to get started, please pause this now, and I want you to have a go at these 2 warm-up questions. With question 1, in your explanation, it's really important that you recognize that no, the velocity of the train is not the same in all frames of reference. All right, you should give some examples there, perhaps draw a diagram. For question 2, you should have received an answer of 12 meters per second. Okay, so if we have one person walking towards a car coming at them at 10 meters per second, we add those 2 together. We end up with 10 plus 2 meters per second, which is 12 meters per second. All right, to get started today, the first thing we need to talk about is this idea of an ether. You might have heard this day to day, into the ether or something like that. Basically, guys, back in the day, they thought that, if heat had to travel through something, sound had to travel through something, a medium, for example, they thought, the radiation or light from the sun must also travel through something in order to get here on Earth. And they called this medium the ether. So this was prior to the 1900s, and it was thought that if Earth was in fact moving around the sun, which was established before this idea of an ether, that means that as we are moving, we must have some kind of ether wind. So this is similar to if you're going for a run, even if it's not a windy day or there's not a wind, you actually feel that air rushing past you. The other idea about this ether prior to the 1900s was that, light would travel at different speeds from different sides of the Earth. So, for example, if Earth was traveling this way with velocity v, all right, if light was coming in the opposite direction, as indicated by this arrow here, we would see the light traveling slightly slower at the speed of light minus the velocity of the Earth. The other thought was if we saw light traveling to the Earth from behind or in the same direction, we would see it traveling at c plus v. We would see light traveling at faster than the speed of light. So people set out to sort this out. They were like, okay, this is what we expect if the ether is in fact real, and relative motion as we understand it, thanks to Newton and Galileo, is the way we understand it, which is what we were talking about last week, then this should be true. So 2 scientists, Michelson and Morley, set out to have a look at this, to see what this was all about. They did this experiment in the late 1900s, and they did it using what's a device called an interferometer, which essentially measures light, to determine if there was a measurable difference in light speed if light was coming from different sides of the Earth relative to the Earth's motion. It didn't. Okay, this was not expected, and this is considered the most famous failed experiment in physics. So they expected that light would move differently because we are moving, all right? Because relative motion tells us that that should be a different speed, but it has been proven experimentally not to be the case. Later on, not too long later, but in the 1900s, this brought Einstein to this idea of some postulates of relativity. So remember, special relativity is a new branch of science. And these were Einstein's postulates. He said, okay, the laws of physics are the same in all inertial frames of reference. So just a reminder there, inertial frames of reference are those that are not accelerating. Another way to say this is saying there's no preferred frame of reference. So the Earth's frame of reference and the Sun's frame of reference might be different, but in no way is one better than the other. Another way of thinking about this again is basically saying that there's no law of physics that can identify a state of absolute rest. So there's no way that you can say, nope, that's absolutely not moving, because it will be moving relative to something else in a different frame of reference. So that was his first postulate. His second postulate, and this is the big one, it's that the speed of light has a constant value for all observers, regardless of their motion or the motion of the source. So this is what the Michelson-Morley experiment showed. Basically, guys, this goes against the idea of relative motion. Because if we think just before, we had that person walking, we had that person walking to the south while we had a car going north, and relative to the person, the car was traveling at 12 meters per second, faster than the car was actually traveling. But this does not work for light. Okay, so this is hard to get our head around. So why is this so special? Why are these two postulates of relativity so special? Mainly, it's because from the 1600s, we have Newton's laws of motion. Galileo, with all his work to do with the Earth's motion and in classical physics as well, we had all of these wonderful, amazing ideas that there's such thing as an absolute true time, and that there's absolute immovable space. And that works in a macroscopic world. We can be like, yep, it is, this time now and is this time then, and that is the same for everybody here on Earth. And we're happy to accept that. I'm doing this at 5:11 p.m. Okay? It's 5:11 for all of you as I say this. All right? It's also true for us that we for the macroscopic world, for things that we can see here on Earth, that is a movable space. But this isn't true after Einstein started doing a bit of research. He realized, you know what? Hang on a moment. Classical physics only holds true in inertial reference frames. Okay, so this is just some of all the insane, amazing work that he did. He also realized that there's no privileged frame of reference, and that everything in our universe is relative. That includes both space and time. And he also realized that, you know what? This classical physics idea is not true for light. We don't have relative motion according to light. Light travels at the speed of light in a vacuum. It does. So in fact, there mustn't be anything in there stopping it. So the idea of an ether was quickly disregarded, and that's when we realized that we have that empty space between us and the sun. So now we call it space rather than the ether. So Einstein had this thought experiment. And this thought experiment, his thought train or Gedankentrain, he was German after all, it's this idea that we have two people on a train, A and B, so Alice and Bob, whatever you want to call them, and they're separated the same distance from the light on the train, and all of a sudden the light turns on. Okay, it turns out that both Alice on the left and Bob on the right, they agree that the light hits them at the same time. So for both of them, they see the light turn on simultaneously. But if we consider an observer C, Chloe, sitting outside the train, this isn't true for her. So even though light is still traveling at C, she will say, hang on a moment, that light is going to hit Alice before it hits Bob, or it's going to hit the back of the train before it hits the front of the train. So we find that these two things are not true. So that means that something kind of weird has happened here to do with the movement of light, and while bringing it into this idea of relative velocity. Now, if you haven't done them already, chapter 10.1, question 5 and question 6 actually have a really similar example to this without light in it. So this is his thought experiment train. Now with this thought experiment train, we're going to see this quite a bit. The idea when light is on a moving object, okay? And we're going to see how it contradicts our idea of relative motion as we continue in this course. But basically, because in this case, in this second case here, Chloe will see it hit the back of the train before it hits the front of the train. In other words, she sees Alice receiving the light waves first before Bob, even though on the train they agree, Alice and Bob, in this example, that they see it at the same time. And this is really confusing because what's going on? And guys, the reason this is crazy to think about is because we cannot comprehend the speed of light. We can't see it with our eyes. So let's consider this scenario here. It's a bit of a question, and pause it if you want to have a go and think about it. But essentially we have two trees. Let's think about the fact that we have two trees and they're separated by a distance d. We have Nathan at the base of tree A, and we have him running at a constant velocity towards Phoebe, which is this way, all right? And Phoebe is stationed in the middle of the two trees. Now, all of a sudden, Phoebe observes lightning striking both the trees. It's a really bad lightning bolt. We see her observing lightning striking both the trees at the same time. According to Nathan, all right, so this is Nathan running very close to the speed of light, okay? Very, very, very close to how the speed of these lightning bolts. According to him, which tree does the lightning strike first? Now, in this case, it's really, really easy to say, well, he sees them strike the trees at the same time. And if you did that and you said that, I don't blame you. Some of you might have said that he would see it strike tree A first because he's so much closer to tree A. If you said that, I understand why you said that as well. I mean, that makes sense in real life. But the fact that he's moving very close to the speed of light, say he's moving at 0.8 of c, so 80% of the speed of light, what that means is, guys, if this is traveling at c this way and this is traveling at c this way, Nathan is actually going to see the lightning strike tree B first because he is, in a way, almost outrunning this lightning strike. Okay, and he actually sees this one first, this one from tree B, because he's running towards it and it's running towards him as well. Now, this idea doesn't make sense day to day. It's not ever something that we would observe because these speeds they're at the speed of light. All right, but this is how we're going to have to start thinking. In chapter 10.3, there's not very many questions. They're really just thought questions and some context questions, but have a go at those before we move on to simultaneity tomorrow.